Hey guys, welcome. Yeah, so if you haven't watched example 0, you should definitely watch it because it gives you a bird's eye view on related rates and some preview of the examples and a feel for related rates generally. But yeah, here in this first actual example, we look at a spherical snowball that is melting so that its radius is decreasing at a constant rate of 2 centimeters per min. Um, and the next example, example 2, we'll look at the same situation, but where the radius is decreasing at a non-constant rate. So here we have subtitle, spherical snowball, constant. Next example, spherical snowball, non-constant. Now, if we continue reading here in this problem, we see that initially the snowball had a radius of 70 centimeters, and the question is, how fast is the volume decreasing half an hour later? So when t is equal to 30 minutes, how fast is the volume of the snowball decreasing? Um, all right. Now, other than having a visual to start, something really nice to do is to write down what you know, what you're looking for. So what we know is that drdt, so the radius changing over time, that rate is constant and negative. Very important to keep track of like negative and positive signs because what you're doing are physics problems. So here in the context, since the radius is decreasing, we need a negative sign. So negative, and it's 2 centimeters per min. And it's also good to keep track of units if you're a good student. And you might have to for the AP exam. You could like consult the AP rubric. But yeah, it's nice to keep units when you're doing related rates problems, at least when you're first learning them, because they're a good way, the units, a good way of checking whether or not you're doing things correctly. Like if your volume rate is measured in centimeters per minute, you know that you did something wrong. Volume should be centimeters cubed per minute, right? Okay, now this is what we know. We also know some other stuff, but like I'll mention that later in this example. Specifically, like we know that like we want the rate of change of volume when the time is 30, and we know that the radius to start was 70, but that's not convenient to write down, so let me just jump to what it is that we're seeking. And what we're seeking is the rate of change of volume, so dv/dt, when t is equal to 30 minutes, right? And here, like, we're already told that the volume is decreasing, but yeah, that's a good way to check your answer too, which is that like if you get a number for dv/dt that's positive, in this question you did something wrong, because if the radius is decreasing, the volume should also be decreasing. Therefore, the volume dv/dt should be a negative quantity, right? Okay, cool. All right. Anyway, after you write down, what you know and what you don't know from reading the question, then draw yourself a quick sketch, which in this case is not very helpful. But after you do these things, which is write down the knowns and unknowns, and you have a sketch, the next thing to do is write a big formula that relates all of the variables. Here, it's the volume formula for a sphere. And the volume of a sphere, V, is given by 4/3 pi r cubed. So yeah, after writing down the knowns and unknowns, and then you have a sketch, the next thing to do is write down a formula that relates the variables, which in this case is the volume formula for a sphere. After you write down your formula, what you need to do is take the implicit derivative on both sides with respect to t. So here, if we do that, we have to write on the left side dv/dt, and then on the right side, we have to write equals, using power rule, 3 times 4/3 pi, and then r to the 3 minus 1 power, which is r squared. All of that, if you do it correctly, 3 times 4/3 pi and then r squared is going to just be 4 pi r squared. But remember, we're doing implicit differentiation with respect to t, so we now have to multiply by dr/dt. Okay, cool. Now, we remember that we have to find dv/dt at a specific time, which is when t is equal to 30. So t is equal to 30. So then we're looking at, on the right side, dr/dt when t is equal to 30. Well, lucky for us, dr/dt in this problem is constant. So whether t is equal to 30 or 20 or something smaller, dr/dt is negative 2 centimeters per min in this problem, right? Because it's a constant rate, dr/dt. Yeah, okay, cool. In fact, since we know that, let's get rid of this drdt evaluated when t is equal to 30 mins, and replace it with what we know it to be, which is -2 centimeters per min. Centimeters per min. And since we're gonna do keeping units, I'll keep units throughout the solution. Okay, cool. There we are, right? And what next? Next, well, we need r, right? And what we know is we need r when t is equal to 30. Lucky for us, because the radius is decreasing at a constant rate of 2 centimeters per minute. We know that by the time t is equal to 30 minutes, 60 centimeters of the radius would be gone. And we know that initially the spherical snowball had 70 centimeter radius. And so if in 30 minutes 60 centimeters are gone, we're left with, in 30 minutes, just 10 centimeters of the radius of the spherical snowball remaining. So that means this r squared will have to be replaced by 10 centimeters and then squared, right? Okay, cool. Now, what does this turn out to be? Well, first, nicely, we can see that dv/dt is going to be negative, because in the product on the right hand side there's only one negative quantity, but otherwise we're multiplying 4 pi and then 100 centimeters squared by -2 centimeters per min, and so all of this totaled will be what? Like 4 times 100 is 400 times -2 is -800, so it's -800 pi, right? And then centimeter squared times centimeters is centimeters cubed per min. And we have a good sanity check with the units on dv/dt. We expected them to be centimeters cubed per min, and they are, and dv/dt is a negative quantity, so all good. Yeah, so this is it for example 1, and look out for example 2 to come. Yeah, cool. All right, take care, keep watching.